Our last video showed a relationship between Z12 and S2, and we created a function or mapping that takes us from the elements in Z12 to the elements in S3, and importantly, all the elements satisfied this formula. Because this all worked, we knew these two groups were homomorphic. They were the same shape. But what if we could show two groups to be equal shaped, something a bit stronger, something we would call isomorphic? Before we show this concept using D6 and S3, first recall our mapping from Z12 to S2, took all of our even elements and mapped them to the identity, and then took all of our odd elements and mapped them to the transposition element. This was all good, but what if we tried to reverse the mapping? Go back from the group with 2 elements to the group with 12. Where would the identity map back to? The 0? The 2? 4, 6, 8, 10? So it's easy to see this map does not go both ways. There is no inverse function. Let's go on with our example using D6. Recall this group as the symmetries of motion of an equilateral triangle, the rotations and reflections. We have the identity element, a single rotation A, a double rotation AA, and then the reflection about each of the 3 axes, the element R, the element S, and finally the element T. Putting all of these together, there are 6 elements of motion of symmetries in the equilateral triangle group. Let's look at the group of permutations S3. We also have an identity or do-nothing element. We also have a transposition element 1 and 2, a transposition element 2 and 3, and the final transposition element 1 and 3. We can also move 1 to 2, 2 to 3, and 3 back to 1, and then the final element moving 1 to 3, 3 to 2, and 2 to 1. If you're not familiar with the S group, you can check out Lesson 4 on permutations. So here we have our 2 groups, E, A, R, S, A, A, and T in D6, and the identity element 1, 2, 3, 1, 2, 1, 3, 1, 3, 2, and 2, 3 in S3. And both groups have 6 elements. Like our study of homomorphisms, let's create a mapping from one set to the other. A good and easy first choice is to always map the identity element to the identity element. Next, let's take A in D6, the rotation of 120 degrees, to the 1, 2, 3 element in S3. R, one of the reflections in D6, to 1, 2, a transposition in S3. And similarly, the element S to the element 1, 3. T, the last reflection, to the last transposition, 2, 3. And finally, AA, the double rotation to the 1, 3, 2 element. Notice something a bit different from our map when we took the 12 elements in Z12 to only 2 elements in S2. In this case, the mapping goes from 1 and only 1 element in D6, which we call the domain, to 1 and only 1 element in S3, which we call the range. And just as important, in our example, we've mapped all of the elements in the domain, and when we were done, we had mapped an element to each and every element in our range. Our map is 1 to 1 and onto. We can see that the 6 elements in the group we call the domain, D6, each map to 1 and only 1 element in the range, S3, and all elements in S3 have been mapped. If the elements under this mapping satisfy our equation, then our mapping is a bit stronger than homomorphic. It is isomorphic. The two groups have an equal shape. So let's take a minute and explore the equation, but use a more intuitive construct and not just math. Let's bring back our triangle group and of course our permutation globes. Notice each of the corners of a triangle have a color that corresponds to the color of the globes. And so we can label the triangle the same way, 1, 2, 3, or red, green, blue. Now, the formula. Remember the mapping should be the same if we perform the operation in the domain, D6, and then map over the results, or if we map over the elements first and then perform the function in the range, S3. We will leave most of the testing to you to satisfy yourself that the equation holds, but here's a quick example. And now think of the colors and how they move. Notice a reflection about the 90-degree axis, which we called T, is really the same as the transposition of the green and blue corners, the same as the transposition element 2, 3 in S3. If we follow that with a rotation, the element A in D6, well, that's the same as following it with the element 1, 2, 3 in S3. If you can demonstrate to yourself that this equation holds, we know that these two groups are an equal shape. Again, we call that isomorphic. In this video, we showed a 1-to-1 and onto mapping from the group of symmetries of a triangle, D6, to the group of permutation of 3 objects, S3, and the mapping satisfied this equation. We considered these two groups to be equal shaped, so we called them isomorphic. In our next video, we will cover some of the characteristics of the isomorphic mapping between two groups. We will see you in that video, and if you like these videos, please give them a thumbs up down below and help the channel grow by telling a friend or becoming a subscriber.